students! Today we are going to discuss about the electromagnetic waves. In this lesson, you will explore the different regions of the electromagnetic spectrum. The different learning tasks set here will lead you to compare the relative wavelengths of different forms of electromagnetic waves. Furthermore, you will discover how electromagnetic waves transport energy and how these waves affect living things in the environment. By the way, I'm Miss Karen, your science teacher. Do you know what is an electromagnetic waves? Electromagnetic waves are also called as electromagnetic radiation. These are waves created as a result of vibrations between an electric field and a magnetic field. Electromagnetic waves are formed when an electric field comes in contact with a magnetic field. The electric field and a magnetic field of an electromagnetic wave are perpendicular to each other. They are also perpendicular to the direction of the EM wave. EM waves travel with a constant velocity of 3.0 times 10 to the 8th power meter per second. They are deflected neither by the electric field nor by the magnetic field, but they are capable of showing interference or diffraction. An electromagnetic wave can travel through anything, be it air, a solid material, or vacuum. It does not need a medium to propagate or travel from one place to another. Unlike mechanical waves, like sound waves or water waves, needs a medium to travel. The EM waves are transverse waves, which are measured by their amplitude or height, and wavelength, which is the distance between the highest and lowest points of two consecutive waves. The highest point of a wave is known as crest, whereas the lowest point is known as trough. Electromagnetic waves can be split into a range of frequencies known as the electromagnetic spectrum. Examples of EM waves are radio waves, microwaves, infrared waves, X-rays, gamma rays, and etc. Let us meet the original players in electromagnetism. Others who laid the groundwork for the understanding of the concepts of electromagnetic theory. Danish physicist Hans Christian Ørsted discovered accidentally in 1820 that magnetic needle is deflected when the current in a nearby wire varies, which is a phenomenon establishing a relationship between electricity and magnetism. Andre Marie Ampere, influenced by Ørsted's discovery, performed a series of experiments designed to elucidate the exact nature of the relationship between electric current flow and magnetism, as well as the relationships governing the behavior of electric currents in various types of conductors. These experiments led Ampere to formulate his famous law of electromagnetism, which is called after him Ampere's law, that describes mathematically the magnetic force between two electrical currents. Michael Faraday made his first discovery of electromagnetism in 1821. He took the work of Ørsted and Ampere on the magnetic properties of electrical currents as a starting point, and in 1831, he achieved an electrical current from a changing magnetic field, which is a phenomenon known as electromagnetic induction. He found that when an electrical current passed through a coil, another very short current was generated in a nearby coil. This discovery marked a decisive milestone in the progress not only of science but also of society. and is used today to generate electricity on a large-scale power station. Joseph Henry, while working with electromagnets in 1829, made important design improvements by insulating the wire instead of the iron core. He was able to wrap a large number of turns of wire around the core and thus greatly increase the power of the magnet. He had made an electromagnet that could support 2,063 pounds, which is a world record at the time. He also searched for electromagnetic induction, and in 1831, he started to build a large electromagnet for that purpose. He was the first to notice the principle of self-induction. A brilliant physicist and mathematician, James Clerk Maxwell, proposed Faraday's electromagnetic induction to happen even in empty space. The symmetry between the fields fascinated him so much. He added two basic principles of electromagnetism. First is a changing electric field in space produces a magnetic field. Second is that changing magnetic field in space produces electric field. Maxwell proposed that the alteration of electric and magnetic fields generating and propelling each other in space can be thought of as a form of moving energy. Maxwell further thought of this form of energy as a wave which he called electromagnetic wave. Using mathematical computations based on his theoretical assumption and the numerical results of Faraday experiments, Maxwell concluded that the speed of electromagnetic waves must be 3 times 10 to the 8th power meter per second. It was only after the death of Maxwell, which a German physicist, Heinrich Hertz, designed an experimental setup that was electrical in nature and able to generate and detect electromagnetic waves. Accelerating electrons produce electromagnetic waves. These waves are a combination of electric and magnetic fields. A changing magnetic field produces an electric field, and a changing electric field produces a magnetic field. As accelerated electrons produce an electric field of wave, the varying electric field produces the wave's magnetic field. Both the electric field and the magnetic field oscillate perpendicular to each other and to the direction of the propagating wave. All electromagnetic waves can travel through a medium, but unlike other type of waves, they can also travel in vacuum. They travel in vacuum at a speed of 3 times 10 to the 8th power meter per second and denoted as c, the speed of light. Now, let's go to your learning task 1. You have to match scientists with their contributions in the development of the electromagnetic field. He contributed in developing equations that showed the relationship of electricity and magnetism. The correct answer is next. Showed experimental evidence of electromagnetic waves and their link to light. The correct answer is demonstrated the magnetic effect based on the direction of current. The correct answer is he formulated the principle behind electromagnetic induction. The correct answer is told a current carrying wire behaves like a magnet. Now, let us explore the electromagnetic spectrum. The electromagnetic spectrum is a continuum of electromagnetic waves arranged according to frequency and wavelength. It is a gradual progression from the waves of lowest frequencies to the waves of highest frequencies. According to the increasing frequencies, the EM spectrum includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. These waves do not have exact dividing region. The different waves are defined by the amount of the energy carried by or possessed by the photons. Photons are bundles of wave energy. Among the EM waves, the gamma rays have photons of high energies, while the radio waves have photons with the lowest energies. On the other hand, in terms of wavelength, the wavelength of a radio waves can be compared to the size of a football field, while the wavelengths of gamma rays are as small as the nuclei of an atom. The waves in the various regions of the electromagnetic spectrum share similar properties but differ in wavelength, frequency, energy, and method of production. Now let us go to the regions of the electromagnetic spectrum. First, we have the radio waves and TV waves. Radio and TV waves have the longest wavelengths and the lowest frequencies in the electromagnetic spectrum. They can be produced by making electricity oscillating an aerial or antenna and are used to transmit sound and picture information over long distances. Next, we have the microwaves. Microwaves are also radio waves of very short wavelength. They are used in satellite communications because they can penetrate the ionosphere. Ionosphere is a layer of the Earth's atmosphere in which there is a high concentration of charged particles. Another one is that infrared waves. The infrared The wavelength of infrared waves is too long to be visible to the naked eye. Infrared radiation is most noticeable when given off by hot objects, especially when objects are red hot. Next is the visible waves. At about 700 degrees Celsius, the shortest waves present can be detected by the eye. These visible waves are what we know as light waves. Visible light makes up only a small portion of the entire electromagnetic spectrum. When white light passes through a prism, it is separated into its constituent colors: red, orange, yellow, green, blue, indigo, and violet. Violet has the shortest wavelength and red has the longest. There are no sharp boundaries separating the various colors. Instead, there is a continuous blending from one color to the next. Ultraviolet waves. Ultraviolet waves are invisible radiation that lie behind the violet end of the visible spectrum. Ultraviolet light has a shorter wavelength than violet light and carry more energy. The sun is our main source of ultraviolet light. Next, we have your X-rays. X-rays are short wavelengths and high frequencies and are very penetrating. They are produced by the rapid acceleration of electrons in X-ray machines that collide with atoms. These atoms emit X-rays. X-rays with long wavelengths that can penetrate through flesh but not bone are used in X-ray photography to help doctors look inside the body, while X-rays with shorter wavelengths that can penetrate through metal are used in industry to inspect welded joints or faults. All X-rays are dangerous because they can damage living cells and can cause cancer. And last, we have the gamma rays. The gamma rays are high-energy waves produced from nuclear reactions. They have shorter wavelengths than X-rays because energy changes within the nucleus are normally much larger than those that takes place outside here. They are more dangerous than X-rays because radioactive substances emit them. For your learning task 3, study the given illustration and complete the missing information on the electromagnetic spectrum. And that will be all for today. Thank you everyone and God bless.